There we go. Hi, good morning. Okay, page for the KWL. And then today's objective. Today is the 19th of January. Today's code is chapter 5. We're doing lessons 1 and 2. Chapter 5, lessons 1 and 2. They're going to be all kind of mixed up today. I know what it says. Today's title is Special Segments and Points in Triangles. Now, if you look at the assignment that you picked up, you're probably going, but this doesn't have anything to do with triangles. The assignment that's out for you to pick up is from a couple lectures ago. Chapter 7, lessons 2 and 3, back when we were doing similar polygons. The assignment for that came out while you were benchmarking, and I didn't want to overwhelm you with, oh my god, I have homework and I have a giant test. So I just held it till you were done with the benchmarks and then handed it to you. So I will identify special segments and points in triangles is what we're going to be doing today. As I catch up, because a few of you are sitting there drumming your fingers at me going, I already wrote this down. You're going to be identifying them by using some definitions of words we've already covered. Words such as midpoint, bisector, and perpendicular. I haven't been able to write perpendicular properly yet all day today. I don't know what's wrong with me. Okay. But first, before we get to special segments, I need to go back a moment and give you one more theorem in congruent triangles. Oh, I just dropped my pen. Back your pen. Don't run away.
Never let go.
Never give up.
Baby, come back.
Any kind of fool can see. I want to write with you because you're red and I like red. Okay. This one is the isosceles triangle theorem. And the isosceles triangle theorem, that was a really bad joke. The isosceles triangle theorem says this. The base angles of an isosceles triangle are congruent. Let's draw our little picture here. So here we have a triangle. It's isosceles because two of its sides are congruent. And so the base angles are congruent. Please note that the base of the isosceles triangle is always that third side that isn't necessarily congruent. It could be. It totally could be. But then that isosceles triangle usually gets a different name, called an equilateral triangle. Okay. So it's the other side is the base. And so these are the base angles. And they're congruent to each other. Legs. Yeah. I never did isosceles anatomy, did I? No. Should I? Just real quick. These are called the legs.
You did that, no?
With right triangles, yeah.
Oh.
Yeah, but these are isosceles. Yeah, they're slightly different because in an isosceles triangle we don't have a hypotenuse, we have a base.
Oh, I don't know what that was.
But the legs are totally the same. Yeah.
Yeah.
Awesome. Thank you for that wonderful side conversation. I really enjoyed it. Thank you. All right, let's go in and start talking about the special segments and points. The first special segment that we're going to talk about today is the mid-segment of a triangle. The mid-segment is a segment, and I'm going to leave some room here on the right-hand side, so follow along with that spacing. It's a segment whose endpoints are the midpoints of two sides of a triangle. That was on the test, wasn't it? Yeah, and like I said, there's stuff that was on that test that I hadn't gotten to yet. Here it is. All right, so let's draw our little figure. So we're going to have some sort of triangle sitting here. And we want a mid-segment, so kind of halfway through this line, and then going to halfway through that other side. Note, because these are the midpoints, this piece is congruent to this piece, and this piece is congruent to this piece. But those pieces aren't necessarily congruent to all each other, you know? Like all four of them aren't necessarily congruent to each other. Note. The mid-segment is going to be parallel to the third side. Yeah. We're going to call it the third side because this isn't an isosceles triangle, and it's only the isosceles triangle that really has a base. So I don't know if this is a base or not, but I know it's that other side that didn't get intersected. They're going to be parallel to each other. Okay? Can you imagine the kind of questions I could ask on this thing? Such and such is a mid-segment. Find the value of x, and then I give you information here with variables and you got to set them equal to each other and stuff. We'll probably be doing those a little bit later. The next word is the median. Median sounds a lot like algebra, where you're trying to find the mean, median, and mode. Yeah. So the median was that kind of halfway point. In geometry, it is going to be the segment connecting a vertex. Remember, a vertex is a corner. A vertex to the midpoint of the opposite side. Okay, here's our little diagram. Oh, that triangle looks funky. Sure, yeah, it doesn't matter how you draw your triangle, okay? You can draw yours looking a little better than mine if you want. Mine's kind of wonky looking. All right, so here's the vertex that I'm going to be going at, and I really don't care how it intersects this other one as long as it does it kind of in the middle, okay? What's really important is that this piece and this piece be congruent, okay?
Also, they have to be equal?
They have to be equal. Now notice, I don't care about the angle of intersection, how this median line intersects the other side. I just care that it does it right at the middle of that segment. Okay? The next side is called the altitude. Sorry, my handwritten notes here off to the side. It looks like I wrote attitude. I don't even... Okay. The altitude, which sounds a lot like a height thing. The airplane was flying at an altitude of whatever. Its height above the ground is whatever. Yep. Okay, and question between longitude and latitude. The lines that go around the Earth.
I know, but which one is?
Which one's which? Okay,
One that goes around
latitude is going to go where the equator is, And longitude is going to go where the poles are.
Okay, I was on this one.
Yeah, me too. And I had to think about this why I was asking and doing with my hands because that was the only way that it made sense. All right, so the altitude, the height of our triangle, we can go ahead and write here height because altitude is the proper name for it. Height is kind of what we're going to use when we start talking about areas of triangles and things. The altitude of a triangle is the segment that goes from a vertex, so it looks kind of like a median, but it goes to a line containing the side opposite the vertex, so the opposite side. And it must intersect at a 90-degree angle. Yeah. We'll take up some real estate here to show you a picture. Note that it's perpendicular to. And that upside down T is the symbol for perpendicularity. Oh, that's a word. All right, let's draw some pictures. Here's a triangle. Nothing too special. We want a segment that goes from a vertex to a line containing the opposite side. So here's, huh? Yeah,
That symbol.
this one,
Yeah.
perpendicular to.
I knew that.
You were testing me. Thank you.
Yeah.
Did I pass?
No.
No? Darn it. I'll try harder. Okay, so here's the opposite side. We're going to put a line through it. Notice how part of the line is indeed covering the side. So now I want a line that goes from this point toward this line, and I want it to hit at a 90-degree angle. There's the altitude. I was about to say attitude. That is the altitude. Now, contrast this for a second. Because notice how it says the line containing, and it's like, why didn't you just say the opposite side? It hits the opposite side, right? The short answer to that question is, not always. What if your triangle looks like this? And what if the vertex you're coming off of is this one?
You draw the triangles?
Yes, please. And now the side, the line containing the side opposite is this line right here. And so the altitude ends up here, not inside the triangle. That is the single weirdest part of altitude. Okay?
So, if it's obtuse, we're just gonna start from the
It depends on which vertex you're pulling your altitude from. If I pulled my altitude from this vertex, this is still an obtuse triangle, mind you, but if I pulled my altitude from this vertex, it would go this way. Not because it's half, but because this is the opposite side and I have to go that way toward it.
Okay.
If this were the vertex, I'd have to go this way. I'd have to go toward this side. So this one looks like it would be outside, but just barely. This one would be inside, this one would be outside. It depends. Okay? And that's the weirdest, hardest thing about altitude. Okay? One final segment type, and then we go into two theorems that have to deal with that segment type. This special segment is the perpendicular bisector of a triangle.
Wait, are those things enough?
Are those what?
3 lines are good enough?
Should be just good enough. What did perpendicular bisector mean?
They intersect.
How?
Isn't it that it lies in half?
Yeah, it divides it in half and intersects it how? What angle?
90 degree.
90 degree. So basically, a perpendicular bisector is going to be any segment that is a perpendicular bisector of a side. Let's draw a picture. All right, there's our triangle, nice and obtusey and scalene. I'm just making that up, I don't know. What we really want is a perpendicular bisector. So I know that I'm going to cut this side into 2 congruent spots. This seems to me to be about the halfway point. And I want it to do that at a 90-degree angle. So I'm going to grab my handy-dandy protractor. And I'm going to mark off where my 90 degree is. It should be about here. You don't have to do this. You can eyeball it, but I want you to see how that 90 degree is made. Notice how that segment doesn't have to go through a vertex. It really doesn't. No one cares. All right? Oh, and it has to be at a 90 degree. We just want that segment, wherever it is, to be in the midpoint of one of the sides and at a 90 degree angle. Seems okay so far? All right, this has some implications for us. This tells us some things. So I'm out of room. I need to go to the next page so that way we can do the 2 theorems that are connected to this particular segment type. No, it will not be enough for 3 lines. All right, the first theorem. I'm experimenting with different bullet types to try to distinguish between what's a definition and what's a theorem. So tell me if it's working out for you as we continue along. And that way I can kind of try to go back and help make things a little more clear. The first theorem that we're going to be working with is called the perpendicular bisector theorem. The perpendicular bisector theorem says this. If a point is on the perpendicular bisector of a segment. Notice how that we don't have a triangle yet, we just have a segment and its perpendicular bisector. Then it, the point, is equidistant from the endpoints of the segment. Equidistant. Equal distance. If a point is on the perpendicular bisector of a segment, then it, the point, is equidistant from the endpoints of the segment. And I got flagged right here with equidistant, question mark. And then it was promptly followed up with equal distance. To which I said, yeah, English is funny that way. We can take 2 completely different words and mash them together and suddenly we have a brand new word. Let's draw what this figure looks like. So here we have a segment. Can I have the names for the end of my segment, please? I heard Z and I heard L. And now we need its perpendicular bisector. We're just going to sketch it in. But we could construct this with a straight edge and compass, couldn't we? You remember doing this?
No.
Oh, yes.
Yeah. Where you had to take a circle and like draw this one and then draw the same one and then you'd connect.
Oh,
Yeah? All right. So here we go. We have our segment and we have its perpendicular bisector. And we're going to grab some point up here and I need a name for that point. I heard R. And I heard the start of the letter Q, so I'm going to go ahead and name that point down here as Q. What this says is that this distance here is going to be the same, equivalent to this distance here, which means those segments are congruent. Before we go any further, once you're done drawing your figure, take a look at it. What kind of stuff do you have in this figure?
It's
Two lines and angle.
We had 2 lines, we got some angles. What else do we have? We could have some reflexive property going on right in here to say that that segment is congruent to itself. We don't have an angle, but we do have a side, side. And with that side, side, we can say that this triangle here on the right is congruent.
to the other one.
So RQL
Oh,
is
make that.
Exactly. This theorem will help us create some congruent triangles, but not just congruent triangles, but what kind of congruent triangles?
Right triangles.
They're right triangles. Ladies.
Oh, amazing. Okay, you put a curvy and
I put a curvy. Where did I put my curvy?
on the
And the Q miss.
yeah, on the cube. On the bisector.
That?
Yeah.
Oh, I'm sorry. Does it look curved? I meant for it to be real square. Is that better?
Okay, yeah.
Okay. Sorry. It's supposed to be square, like really perfect. And I can't draw straight lines.
Yes, it's okay. I can barely draw a circle without it having a slant.
Woo! I use my ring and I trace my ring. All right. Sounds okay so far? But what else do we have? Imagine RQ was not there. What would we have?
What?
The bisector.
Imagine RQ is gone.
Oh, RQ.
Uh-huh.
What do we have now?
We
A
have
whole
a
triangle
line
miss.
segment.
A
We have
whole-
just the line.
We have a whole triangle. We have this right here. But what kind of triangle is it?
Isosceles.
Yeah, isosceles, because these two are congruent, but I don't know what's going on here. So if you were asked with this setup to prove that this triangle is isosceles, this theorem can be that missing puzzle piece for you. Make sense? Okay. All right. There's one more theorem that we get from this. Let's take it in space as the picture. This theorem's name is the converse of the perpendicular bisector theorem. I know, right? These names.
Is there a short? The CPBT?
Sure, you can call it the CPB. That's going to mess with my...
I'm sorry, ma'am.
That's okay.
May I get a photo of you?
Working hard at work and lecturing, that'll be perfect for me. Come on in.
Ma'am, I actually just need like a portrait.
A portrait.
Yes, ma'am.
Can you give me like 5 minutes?
Yes, ma'am, I sure can.
Appreciate it. Thank you.
Thank you.
All right. The converse of the perpendicular bisector theorem says this. Okay. Where does that word converse seem familiar from?
What?
Converse. Where's it familiar from?
Oh, the shoes.
Oh,
The
with
shoes.
The theorem. Not the theorem.
It was
but
from,
the P's
a
and the
lesson.
Q's.
Yeah, the P's and the Q's and the conditional statements
Yeah.
way back over here.
when we first started.
Back when we first started, when we were little fetuses doing geometry. We were babies. All right, how do you form a converse statement?
Form by exchanging hypothesis and the conclusion.
Exchanging the hypothesis and
Yeah,
conclusion.
you exchange the hypothesis and the conclusion. You switch the P's and the Q's. So we just need to figure out which one is the hypothesis and which one is the conclusion of the statements above and write them in the opposite order.
The if is now going to be the same.
Exactly. So it's going to say, I'm going to read the one from above, okay? I'm sorry, that's going to be a little off frame. If it, what did it refer to?
The point.
The point. And not just the point, but we need to say a point to stay real general at first. So if a point is equidistant from the endpoints
It's not a word.
of a segment, what's not a word?
Equidistant.
It is a word.
It is?
It is a word.
If it was, so if it wasn't a word, you wouldn't use it.
Well, I don't know. I've made up words in my time. It is a word that we get by mashing together two other words. English does that a lot because YOLO. Then it, the point that we were talking about in the hypothesis, is on the perpendicular bisector. I can't spell today. Look, I'm nervous about the photo, okay? The perpendicular bisector of a segment. Let's knock out the example. Should take me about 2 minutes or so.
Okay, I'll just sit here.
Yeah, come on in. Relive your glory geometry days.
Yes. They were glorious, I suppose.
They were super glorious. All right, here we go. The example tells us to find AB. Notice how there is no symbol attached to the letters A and B. That means that we're not looking for a segment or a line or array, but we're looking for the distance between those 2 points, the length of that segment. And here's what the figure looks like. So I have B up here, I have C here, I have D down here. A is going to be this way. I'm told that there's a right angle here. Those two are congruent, and this distance is 4.1. And that's all I'm told. And from that, I'm trying to figure out that length. It's not showing up very well. Let me use a darker color. What do I know?
That C and A
I messed it
is
up.
like the same.
That CA is the same line?
No, like CA.
Uh-huh. Oh, it's congruent to itself?
Yeah.
Yeah, we can totally say that. Yes, it's congruent to itself. And now I have some triangles.
This is the same thing we did at the top.
Yeah, it's the same sort of thing we did at the top. We have two triangles, side angle side, right? Or leg leg because they're both right triangles.
Is it?
Give us that they're all congruent, which means these two are congruent,
So then that's
Forward.
which means this is also 4.1. For that example, we used side angle side or leg leg. You could also use this perpendicular bisector theorem. I guess since you want us to abbreviate PBT.
Peanut butter time.
Peanut butter time.
Yeah.
Perpendicular bisector theorem, which said that if this point is on the perpendicular bisector, it is the same distance from the endpoints, which meant that AB had to be equal to AD. And AD is 4.1. Therefore, AB is 4.1. And we have this wonderful property name that we used right here. I just used the transitive property of equality.
Nancy, no me cabe.
Right, smaller?
Just put prop
Yeah, prop
equal,
of equal sign.
equal sign to it.
Thank you very much.